I'm going to start where we left off. Kind of a different approach.
Later during break. But you know what I mean? I'm not the only one asking.
You want to ask a question about 6.8? Sure.
Are you recording?
Skin, the value for your skin. If you recall, you end up not resolving it. Just
I think it's going to take me a second to figure out what 6.8 was. There's no Horner time, so it must have been a drawdown, right? No, we have Agarwal effective time.
We're using the linear slope. You don't get to read everything.
Oh no. Then I can't do it. You know what? It's not going to read it. I'll email it. Stupid thing.
This skin.
I don't see where you're.
I mean the skin. You have to move some of those things. No.
I'm in the emails.
No. Look at the skin there. I get one of those graphs.
Are you saying SKIN?
SKIN, yeah.
I don't remember doing anything with skin. Here? Here's where I did all my calculations.
The value of the skin. You can calculate the skin.
We didn't find.
All cells here have a letter and a number. Tell me what letter and what row and what column.
Say. I'm not saying no.
Skin.
Did he calculate for the skin?
I don't see skin.
Where?
Oh, okay, yeah, skin. Okay, there's nothing there, is there?
Yeah, we didn't.
You didn't calculate for it. I don't know.
Okay, so let's see what it's a good thing I'm not recording because I'm sounding really stupid. Okay, so we had a produced time. Okay, here it is. This is the one we had to correct because there was a misprint in the book. Okay, so we got a buildup. And I can tell by the type curves that we have linear flow. We have no radial flow, so we don't have any perm. Right? And we do have a fracture conductivity. And so, and we were given a perm of 0.1 millidarcy so that all we can do with this problem, this is good because this is will lead into our lecture tonight. And in the normal situation, you can only get square root of KXL. Boom. This cell right here. Okay, that's the normal situation. Anytime you have pressure or rate data that's linear with the square root of time, you can get this product. Now, in this problem we were given a perm, so we back calculated a frac half length. Now, yes, I can tell you what the skin is. I'll record. Well, let me see if I can't find a graph first. I think I can do this quicker. Yeah, no, it's a finite conductivity. So this is a tough question. I'm going to have to pull up a Barré graph. Let me see if I can't find it. Let me open my textbook while I'm here. am looking for Bree. Here it is. Okay. Here's the answer to your question. It's right there. Okay, it looks like I've done a linear fit. So this is Lee text figure 6.39. Am I recording? I am now. Preparing to record. This is good. This is a great way to start the class. Still okay, recording. I'm 2 seconds in. Now, in a situation where we would want a skin, if we have a fracture conductivity, they are interrelated via this graph. And it is in the Lee textbook as noted by that column heading, or that chart heading, figure 6.39. Now, it looks like I've done a curve fit for this. And I call it Bree, because he's the author of the curve fit. So given a frac conductivity, I can tell you RWA over X sub F. See that? And what is RWA?
The apparent wellbore radius?
The formula.
It's
RW times
e to the negative 2s.
Negative S.
Negative s.
That 2s that you're thinking of comes from the type.
E to
the minus s. So the answer is yes. So I can interrelate skin if I have frac length and frac conductivity. Now, you notice this graph right here levels off up here at the infinite conductivity end. In that case, I have a formula that I have memorized. And it's in our textbook. Okay? So where that curve asymptotes at the top is just this equation right here. The skin is conductivity. Now, I don't know that this has any utility. I can fill in that yellow square. Okay? Because I know frac length and I know frac conductivity. So I can knowing conductivity, I can get RWA over X sub F using this function Bree. Bree CFD. I'll give it its CFD. So let's see if I can multitask. Now, when I got two spreadsheets open and it has the same software, I may have a little trouble here. But what I'm going to do is I'm going to copy and then come back to my worksheet and paste. Okay, and it says name, so let's see if I can actually, well, here's what I'm going to do. I'm going to close this spreadsheet. I am going to figure out where I have this curve fit, okay? I'm just looking for my curve fit. Here, that's easy enough. It's a module that has two functions in it. Okay, so let's, you're not going to really need this. Now, I'll show it, it'll be recorded, but I'm now going to close this module. And I want to reopen our workbook right here. And then I am going to import Bree. Here he is. Okay, now I have Berea in my module. So we're doing 6A. So we came up with a frac conductivity of not 500, not 100, but a frac conductivity of 25. Is that in a cell anywhere? I don't think it is. Okay. So CFD is 25.
Is that the same as sigma FD?
Sometimes. It's dimensionless frac conductivity. You got to look at the definitions. There was a period of time when the University of Tulsa and some other institutions were putting out a lot of stuff, and there was a sigma FD, but sigma FD in somebody else's literature meant something else. There was a crisscross. I stick with CFD. And also, there's another paper that has F sub CD. So, you got to be careful.
But we're talking frac conductivity.
Dimensionless fracture conductivity. Okay, so I'm gonna actually reopen my other textbook. Recent. Where is it? New. Open. And just copy the figure over here. So that we can see what we're looking at. This one looks even better. Base. Okay. So there's the function we're doing. Now we know CFD, so I'm going to get RWA over X sub F. Here's where I cut. Oops, where am I? CFD is 25. So now equals. Well, I got to close my other one now. I've got the picture I want from this, so I'm going to close it now. If I got two spreadsheets open and it gets confused about where I'm trying to get a VB module open. Because a lot of things are duplicated, and they could be different. Okay. Equals Berea CFD. My frac conductivity is 25. So RWA over X sub F is 0.46. Let's just plot that point on our curve. Be really fancy. This is what problem? Example 6A. Its X series is frac conductivity, 25. And its Y value is, by my curve fit, is that value right there, 0.46. Now with that up here, it looks like it's a line, so I've got to find the series now. This is always tricky. The only way I know how to do this is put the legend back in. Quick layup. Okay. I got to put the legend back in and then format that data series, and then I want it to have a marker. I don't need a line. I need a marker. Marker options. Build in. There we go. There's my point. So it's fairly high up here. It's almost 0.5. This asymptote's at 0.5. So I can probably use this equation to get away. See? So, but let's go ahead and use this number, because in general you might have a CFD that's much lower. Give her some of these pennies. So now I know that's RWA over X sub F. Okay, so now RWA is RWA times x of f times x of f. Don't we have an x of f? Yeah, 225 feet, right? So now I got an RWA. So now I can calculate a skin. If I got RW. I'm pretty sure I do. It's 0.25. RW e to the minus s. So skin is minus the natural log of RWA over RW. Minus 6. Voila.
And that's for the fracture, or it's for the well. I mean, not really, huh?
It has no meaning.
Yeah.
That's why I left it blank. Because what we really want to do to characterize the reservoir is know the fracture half length. So this is probably the only application I can think of is let's look at our type curve. If you had semi-log data for a well that was hydraulically fractured, but we're missing all the early time data. Now this would happen not on a pressure buildup or a pressure drawdown where you lowered a bomb in the hole, but where I would see this is, let's say you shut in a well, a gas well, and then the pumper every week told you what the surface shut-in tubing pressure was. Okay? So maybe you have that for week 1, week 2, week 3, week 4, and maybe due to this might be a situation where they haven't hooked up the well yet. Okay? Oftentimes they'll let you produce and flare for a set period of time, and then you have to wait for the pipeline to be hooked up to the well, right? So you may have data that's wasn't there on purpose. They didn't lower a bomb in the hole. They don't have time and hours, okay? Maybe the first data point's in 1 week, and then you have subsequent weeks after that. So on this type curve, time-wise, maybe you're way off here to the right. So then you actually have radial flow. Okay, so what you do is you convert all your surface tubing pressures to bottom hole pressures. And then you plot bottom hole pressure versus the semi-log of time. If you're doing a drawdown, if you're doing a buildup like I'm just talking about, you would have to incorporate T sub P into a Horner plot. From that Horner plot, you could get P star. From the slope, you could get perm. And from P sub 1 hour, you could get skin. So then, if you had skin, and normally the only thing I would ever do is I would take my skin, I'd calculate my RWA, I would multiply it by 2, and that's a good approximation for fracture half length. Because given the example I just gave you, you wouldn't know fracture conductivity. Now, if you believe the service company report that said you had a fracture conductivity of, dimensionless fracture conductivity of 200, then you could use this graph. But in all the real world data that I've ever analyzed, even though I've gone to the trouble of done a curve fit to that graph, I've never really utilized it. I either have early time data where I can calculate the frac length and use a type curve and see what my frac conductivity is. But really, for reservoir characterization, I want fracture half length and fracture conductivity. Skin is really only what it was originally intended for, and that is for invasion and damage. Okay? It doesn't really characterize the reservoir or any of its properties. For frac wells, I'm after frac conductivity, I'm after fracture half length, and of course I'm always after permeability.
Now I'm not concerned. How many experience linear radial flow in pre and post fracture situation?
In a pre-frac test,
Can we experience both linear and radial flow in a pre-frac test
and
post-frac test?
how are you going to get linear flow in a pre-frac test?
It's naturally fractured.
There are reservoirs in the world that are dominated by natural fracture production. But in my opinion, it's less than 1%. And I don't cover how to analyze buildups and drawdowns in naturally fractured reservoirs.
So we just assume pre-frac it's going to be unfractured radial flow.
Yes. So the only thing you're going to get out of a pre-frac test is one of the big, huge things you want, and that's permeability. And P star, initial pressure. Okay, so in my opinion, in most reservoirs, you run a pre-frac buildup to get P star and permeability. And you need all those numbers, plus a defib, to see what pressure the formation will break down at. Then you're ready to design your frac job and proceed to get a commercial well. Unfortunately, most of what we're working with today are shale reservoirs. And we get nothing, absolutely nothing, as far as production until we frac the well. So there is no such thing as a pre-frac drawdown and buildup.
So basically the P star, the P asterisk, the main purpose of getting that is to get our initial pressure.
Initial pressure. Of course, remember when we're doing reservoir engineering, we have a material balance with P over Z versus Q. It tells us how much gas is in place. So, and again, I don't think gas in place is as important as permeability. If permeability is 1 nanodarcy, I don't care how much gas is in place. You're never going to get it out. So in my opinion, permeability is the most important characterization parameter of a reservoir.
I apologize. Sorry, go ahead. I was going to say, I was trying to catch up on what you had done the calculations to back calculate the skin, so I don't know if this was asked, but if you don't know the permeability and you don't have pre-fracture data, how do you go about?
That's what we're going to do tonight.
Sweet. And as an add-on to that, how do you estimate P star if you don't have the pre-fracture?
Okay, initial pressure. That's a good one. The Barnett Shale. Okay, so we didn't know what the initial pressure was for a long time. We didn't get anything out of on treated wells, but remember that we can get a P star from a buildup in linear flow. It's called MC time.
Okay.
MC time will
Right.
extrapolate to a P star.
Okay. Is that a valid P star? I guess
Yes.
is the question.
Yes.
Okay. Okay. How about if you have it like a set of pre-fracture data and post-fracture data, and you analyze them, and you get different P stars, or
I've
should they be
never
the same?
seen pre-frac and post-frac data agree.
Okay. Well, then what would you think about that?
Well, that's what you do, is you think about it.
Okay.
You try to explain. But as an example, if you're doing a laboratory experiment where you are running a capillary pressure measurement, and you invade with one fluid, then have it drain back out, capillary pressure curve, this may be outside of the realm of most of the students in the room, but the difference in those two curves are hysteresis. You never can retract the way you went in. Mm-hmm. And that's where you kind of use judgment. But it's typical that I would never look at a P-star from a radial flow buildup and a P-star from a linear flow buildup, because if you're talking about shale reservoirs, I'd never have the radial flow. Okay? So I've never ran across a P-star comparison.
Okay.
In the real world.
Okay.
Yeah.
But the key benefit of the MC plot is to find that P-star.
Yeah, and square root of KXF. And we're going to play with that, how we're going to get the full utility out of that coupled parameter. I got an eraser tonight. This is tonight's lecture. We can always get that.
Yeah, I have a question as regard that, what you just wrote. I went through your formula in the Excel sheet, and it seems not to be tallying with what I have in the textbook. Can you go to, sorry, I'm trying to reference you. Can you go to the square root of k SF in your spreadsheet?
40.93. I can tell you right now, it's this equation right here. Although I'm using a little bit different nomenclature. But 40.93 means I got a constant rate, which means I got a pressure buildup or a pressure drawdown. So 40.93 reservoir temperature, my slope of my pressure versus the square root of time, or delta pseudopressure over rate if you're normalizing. H, porosity, viscosity, and total system compressibility. It takes a lot to get it. Okay? That's the equation that I'm using right there.
Okay, then it's different from the one in the textbook.
Then what?
It's different from the one in the textbook.
No, that equation's in the textbook. The one I just put up here, that's in the textbook. 40.93?
It's on page 142.
Yep.
When I saw the porosity was in the numerator.
Well, now you got to remember that I'm always using pseudo pressure. So the variables may be a little bit different if you're using apparent pressure. There'll be a B sub G, that's the dead giveaway. If I'm using a formula, there'll never be a B sub G, because the viscosity is incorporated in the Z is incorporated in the pseudo pressure.
Right.
Just come again with that. So I didn't get you.
What I said is, if I'm calculating square root of KXF, or if I'm calculating perm, the fundamental equations we've been using in here have to do with the slope of either radial flow or linear flow. In the equations I use, there's no B sub G. There's no formation volume factor. Now, the textbook is chock full of equations with B sub G in them. But if you look, they're using apparent pressure or pressure squared. There's 4 ways to analyze pressure buildup. Apparent pressure and pseudo pressure will always give you exactly the same answer, because apparent pressure and pseudopressure are related through a constant. It's just a technique to get, instead of numbers in the billions, to numbers in the thousands. Okay? But there's a linear relationship between those two. Using pressure or pressure squared is going to give you the wrong answer. They're approximations. But they're left over from an era when we didn't have computers and couldn't calculate pseudopressure from pressure. It would require, manipulating and looking at graphs and entering numbers, and it was very tedious. So a lot of people use pressure and pressure squared approximations.
But that slope, the VF, that's the same as the ML, the linear slope.
Yeah. Yes. Like I said, I'm using a little bit different nomenclature.
Vertical fracture.
Yeah.
What's the CR?
Constant rate.
Constant rate.
Constant rate means I'm measuring pressure. Constant pressure means I'm measuring rate. And if I'm let me kind of highlight here. If I'm over here, you see you got a different number, 64.27. And in both of my plots are the same, delta pseudopressure over Q. But this is assuming that I'm measuring rates, but I'm subtly normalizing it because I have a slight change in pressure. Over here, Q is basically going to be constant for a constant rate. But what I've done is I've made the equations the same so that in one you'd have a pressure term and one you'd have a rate term. We'll manage with it when we come to it.
I use the same equation that's in the book for my calculations, so I'm not sure what he's talking about.
Well, if you're truly using a constant rate, your rate will be in your equation.
I'm just saying the porosity's on the bottom and calculation.
Are you saying that I had this wrong?
Well, he said it was in the numerator. Is that what you said?
Yeah. The one where you've explained the BG. I can't find the BG in the equation. So I think that makes sense.
So you're saying my porosity is in the wrong place?
No, I'm not saying it's in the wrong place. I mean the one they use in the textbook have BG in the equation. Yours don't have a BG.
Mine doesn't have a BG.
Yeah. So that
We use the equation on page 142, not the PG equation.
Where's my Xbox? Where did this come from? Well, I know how to get rid of it. I thought I had my textbook open. I think we're wasting time. We'll pull these equations up when we need them. Okay, any other questions about 6A?
if SE over SF is infinity, I wouldn't solve that.
I'm sorry, what?
If the ratio of XE over XF, the fractional length from our plot, that plot, if the ratio is infinity, and
We don't know. We don't know.
what are we going to equate it to?
Pardon?
What are we going to equate it to? Like, we equated that to 5.
You can only get the ratio of XE to XF if your data crawls up one of those spines.
I'm assuming it crawled down to that infinity number.
Why would you assume that?
I did an exercise at the back of the book, but it didn't crawl up to that point. But I'm assuming.
Okay, let's just take this a little bit further. If my data point gets to here, where my mouse is, I know that XE over XF is greater than 1.
Yep.
See that? Because I didn't go up that, see? The more I stay on the radial flow, as I pass that stem, I know that XE over XF is greater than 1.5. And as I pass that stem, I know that XE over XF is greater than 2. So you can always do an XE over XF is greater than. one more time. I've never seen a real world example where the data breaks east. It always breaks north. I've never seen an example where x of e over x of f, where, let me restate that. I've never seen linear flow break into radial flow. The textbooks examples are all simulations, but in the real world I never see that.
Okay. What about like this data here? It's in between 3 and 5.
And so interpolate.
Okay.
Just like on these frac conductivities. Now, the way they give us these problems, again, they input into the simulator. I'm looking for my frac conductivity type curve. I don't know why I have two of those. Here it is. You can tell the simulator the input was 25. Okay? And then they showed us what the data would look like so that we can back calculate it. But in the real world, we're not going to get exactly 25. We're going to get some data set that's in between two of these curves, and we're going to have to interpolate. Except tonight, we're going to use this equation and find out that even if we don't have a type curve, we can get our fracture conductivity from an intersect. Okay, we ready to move on to 6-9? All right. Now, we did kind of something illegal because we independently picked a T sub D multiplier and I'm going to call it a P sub D multiplier, but it's also a 1 over Q sub D multiplier. Okay? We actually, it was a multiplier, we divided by our rate into it, and this is a true multiplier. Both of them are multipliers. One of them we multiplied by time, and the other one we took our constant and divided rate into it. Okay? These two are related, and we ignore that relationship because they have K and XF in them. So we're going to do this a little differently. We're going to run through our whole analysis, showing that they're related, and we're going to show that that relation is based on this linear relationship here, which I'm going to improve on. So I'm going to improve my linear relationship. I'm going to solve for the square root of KXF, just like we did in the previous example. And then I'm showing that once you pick a perm, then that is your P sub D multiplier or your 1 over Q sub D multiplier. There's a perm in our P sub D or 1 over Q sub D. Okay? Here's Q over Q sub D would be for this case, would be our multiplier. There's a perm term in there. Also, if we're doing constant rate testing, there's a perm, but no XF. Okay? But once you do pick a perm, I don't have a T sub D equation, but I know here, it's right here. Okay? A perm and a frac length. If I rearrange that and solve for the multiplier, see that? So once I pick one, I'm forcing the other one through this coupled parameter that I'm going to solve for because I have this linear relationship versus the square root of time. Okay? Now that I've said that, let's do it. The first thing I want to do is I notice that I have kind of a subtle curve. You see how the middle of my data points are above the line and the tail end of my data points are below the line. Okay? So I've got a subtle curve. Now, who thinks they know what I should do? Who's got an idea? Shall I leave it like it is?
When we did it the first time, I picked a smaller subset of the data.
Yes, and how would you pick that smaller subset?
Well, I zoomed far into kind of the earlier,
Yeah, that's a good technique.
and then I just kind of, I guessed on a certain number of points and looked at the R-square value of the trend line and then kind of messed around with the number of points until it was optimized.
That's an excellent technique, okay? That's an excellent technique, but I'll show you just one step better.
Okay.
Why don't we use the linear derivative and let that guide us to picking the points? Okay? Sound good? Let's calculate the linear derivative. Let's see if we have a heading for that. That's good enough. Okay, so it equals, do we have time and the square root of time? Yeah. Here's time, and here's the square root of time. I never gave it a heading. SQRT. I tend to not spell some of these out, and the reason is that in my Visual Basic, SQRT means the square root of time, and so. Okay, so we have the square root of time and we have time. So our straightforward derivative is delta reciprocal rate. The way we've been doing this is we would grab it in the middle. dy dx. I missed my equal sign. Equals, open a paren, dy dx. dt. And time in hours. Times the square root of t, and I'm going to grab the square root of t in the middle. This isn't numerically correct. I should actually calculate an average time between the 2 points I'm getting and take the square root of that. But this is quick and easy. And I can see that they're all about 5.3 in this region right here, and then they tail off. This last point's not a valid point. So let's plot this on this. Or do I have a type curve? Let's put it on our type curve. Select data. Add. Until we discovered derivatives, about 20 years ago, what you just talked about is exactly what we did. And again, I don't know how to access my data without putting a legend in here. And I want to put it on the secondary axis so it shows up, and then I got to say that I want markers, marker options built in. How come they don't show up? How come my data doesn't show up? I put it on a secondary axis. Where's my data?
It's invisible. Like literally
Yeah, but
it's got an invisible marker.
look at it. I just said it's built in. I want this. It's showing the marker.
Oh, sorry, I was looking at series 1.
Your T is so big compared with the TD.
Oh, yeah. Because I was going to put it on the other graph. I should have been using TD. I got you. Thank you. So now I'm going to grab it again. Somehow. So if I format the data series and then ignore that, I still have it highlighted up here. and I can drag time to TD. Now it won't show up? No, because it's, that's why I should have put it on the other graph, because it's raw data. It's not fit for, so let's define it so it's ready for, instead of time reciprocal rate, I'm going to use T sub D, except for I don't have a square root of T sub D. I can handle this. Now why does it show up? Because I didn't, it's not plotted versus T sub D. There we go. I finally have it on my graph.
Can I see your equation again on H?
I went from raw data, delta T and delta reciprocal rate, to what we currently have for dimensionless time and dimensionless rate, which we're going to change, but we can still get a flavor of what the linear derivative looks like. And so we're going to kind of use both techniques, but we're actually looking for a straight line. The way to make this line straight is squinch the secondary Y scale, but you can see that basically the first 2/3 of the data is relatively flat, and then it tails off south. So now let's look at our actual data here, and as was said earlier, let's zoom in. Let's go to 40 and 0.06. Let's copy this first so we can look at that. Let's just go to 20. And then over here, let's just go to 0.06. 006. And then instead of using a regression analysis, or we'll continue with the regression, but we don't have that slope. Is this just the, yeah, this is just we're going to have to start here with slope. And the slope we want, is this even labeled right? Is this 1 over Q or 1 over QD? It's reciprocal rate. We borrowed the graph from them. So this is just 1 over Q. So we want the slope. Now, here's even a third way to do it. Let's look at our running slope. Reciprocal rate divided by dx, open a paren. So reciprocal rate versus the square root of time. Here's a running slope every 2 points. And I'm just going to see if I can't throw that on this graph right here. I can't. I'm making a mess here. I'm fighting having to I'm going to get rid of the trend line. I'm trying to zoom in on this data. Here's our original plot. I'm moving it out of the way. Now I'm going to zoom back in a little bit. Let's just put a line on here. This is always my hardest thing to do in class, is find shapes. Okay, so this is the same observation that you came up with. We look at our early time, we can get all of our data on our data points. And our derivative curve says that it tails off at the end. And forget that I ever ran this running slope. Let's just make a decision here and use a slope. We can change this, but let's get a slope for the square root of time up to 15. I'm going to highlight this. Okay, so what is our slope here for the data points up to the square root of 15? Equals the slope, known y's, is reciprocal rate. Known x's is the square root of time. When we get done with our analysis, we want to use a little bit more data. I must not have them matching. It's got to be exactly the same array size. Okay, so now we have a slope to this data. And I'm going to display that data. I'm going to delete this because this is I'm going to display this on all my data. 0 to 90. And of course I need an intercept too. And I'm going to use this intercept that I'm about ready to create with this equation right here. I am going to use the intercept to calculate my fracture conductivity. Eventually. We got all night. I never feel rushed in this class. Okay, let's plot this. It's equal to the intercept, F4, plus the slope, F4, times my x value. Now let's put this on here. Select data. And we don't need to give it a name. Okay, and it thinks it's 2 data points, so now I got to turn it into a line. The marker none, line solid, black's fine, it's a little fat. There we go. Okay, so this is the original graph that we had in class that had my regression analysis on it for all the data points And then it has this one for the first 20 some odd data points. Now let's look at this zoomed in. Let's look at it up to 50, just for the heck of it. And if we go to 50, we need to only go to 0.04. 0.004. And I am going to get rid of my regression line on this zoomed up plot. Okay, so this is the technique you were basically talking about. It's my early time data, fits very well. And then it gently moves away from that straight line. Now, I don't have, at this point in time, I don't have a lot of justification of why I did that, but let's move forward. Let's move forward until we can actually get a derivative on our kind of tie in why we pick this data. And frankly, we're not going to really have good justification for this until we use some superposition and not only look at this on reciprocal rate square root of time, but use the superposition to convert the time from a constant pressure solution to a constant rate solution. We're going to do all that tonight. Like I said, we're going to be very thorough on this. I'm going to try to delete those lines. Okay, what is this? It's my original rate time curve. Okay. We have our type curve match from last week. We've added our derivative data, and basically in class we've said that we're not going to use these latter data points to find an early time straight line that we're going to use to calculate the square root of kxl. Okay, we've got a slope, we've got an intercept. We can calculate the square root of kxl. This is going to be our couple parameter that we're going to drive with. So we've got the equation right here. The square root of kxf, we use this equation. We don't really have a plot of delta pseudopressure over Q, but we have a plot of 1 over Q versus the square root of time. This is truly a constant pressure plot. So that my square root of kxf is missing a delta pseudopressure term. I can add it into the column, but we'll figure out how to put it in here easily. So, let's use this equation. I'm just going to leave the pseudopressure off and then I'll figure it out later whether I want to multiply or divide. I know the number's about 100. Reservoir temperature. We made up 240, didn't we? To get a low error for V sub G?
Yes.
Divided by, in the denominator, we have our slope, our height, and then in parens, our porosity. We're using our viscosity. We don't have to. We need to use theirs. And the total system compressibility. All that's raised to the 0.5. Then I close my paren for my denominator. And it's a really large number, so I know I've got to divide by delta pseudopressure, which is this number right here. and I get a number about 100. .1 millidarcies to the 0.5 feet. Okay, so does everybody understand how I figured out? I mean, if I would have, instead of plotting reciprocal rate, if I would have multiplied every one of those numbers by delta pseudopressure, then it would have been a plot of delta pseudopressure over rate. So delta pseudopressure would have been the numerator of my slope. My slope's in the denominator, so that's why I ended up dividing by delta pseudopressure term. I could longhand going through, adding an extra column and showing that that equation works if you put delta pseudopressure in there, but I think you get the gist of it. Okay, now here's what we're going to do next. We're going to work with our type curve, but we're not going to allow what we did last week. Last week, we independently chose our T sub D multiplier, and that should be T sub D x sub f, shouldn't it? Our T sub D multiplier and our reciprocal rate parameter multiplier. Now, this week, we're going to pick a perm. Who wants to pick a perm? We can use the perm we used last week of 0.0146, or we can use the one the textbook used of 0.01. Let's use one or the other. 0.01. Okay? Once I pick a perm, since I have the square root of kxf, I know x sub f. X sub f is just this coupled perm, and divide out the square root of the perm. So that gives me 902 feet. Okay? I don't mind adding the units here. Millidarcies and feet. Okay? Now, if we know our perm, or we're picking a perm, then we know our Q sub D multiplier. We went the other way. We took the multiplier and we calculated a perm. And this equation up here should look just, see, with the 1422, should look just like this equation. Right here. Let's get everything very neat. Okay, so I want, what am I doing here? I'm multiplying Q times Q over Q sub D. So up here where I have 80, I want KH delta pseudopressure divided by 1422T. We picked the perm, 0.01. I've got my delta pseudopressure labeled tonight, divided by 1422 times 460 plus the reservoir temperature. Close my temperature, close my denominator, and I get 54 instead of 80. You see that? I got a slightly different number. Let's take a, we're not done yet. Let's take a sneak peek at our type curve. See, it's not even on our type curve, but I'm not done yet. Once I pick a perm, oops, we're down here. Color of the night, purple. Once I pick a perm, this is our new word. I've got a slope. It gives me a square root of kxf. We pick a perm, we get a frac length. With a perm and a frac length, we force our Q sub D match, and now we're going to force our T sub D match. So we're going to rearrange this equation right here that we got right from the textbook, and I want to solve, I want to get the reciprocal of this. And I didn't put it on my sheet here. I want to solve, I want t sub dx sub f over t sub t, or delta t, so that when I multiply by delta t, I get t sub dx sub f. So I'm going to practice, and then I know that the number I'm looking for is about 0001. Let me just practice down here and then I'll move it. Yeah, it's just, I'll algebraically derive it. X sub f times phi, no, x sub f squared. I'm going to square both sides. And I got x sub f squared phi mu c sub t. And now I got to put this upside down. So I'm going to put 0.0002637 k. Yep, is going to equal t sub d x sub f over delta t. I'm pretty sure I got this right. So now my t sub d multiplier is 0.0002637 times k. We can change it, but this is what we're using, 0.01.
We actually calculated the K.
I know we did, but now...
I'm saying last time we were...
Yeah.
Okay.
We're redoing it. We're not going to accept that.
Okay.
Here's the thing. Let me sit. Here's the big change from last week to this week. Last week we independently selected T sub D match and a Q sub D match. I'm saying we can't do that.
Okay.
If we believe that we have this couple parameters, the square root of kxf, once you pick one, you've picked the other. You can change the perm. Now, what we're going to do is we're going to play with the perm and see how our data move on the type curve. But once I get in with this equation, we're going to see how it moves that data back up automatically. K divided by, I'll put it in order, phi mu c sub t x sub f squared. And we should get a small number. We do. Let's take a peek at our type curve and see we're back on it. Now, we're going to play some more with this, and then we're going to redo it using superposition in the constant rate solution. Okay, so it looks about like it did last week. But now I am going to change this one parameter, this D highlighted. And let's see what happens, because one of the questions I got by email is, is it possible to find x sub f when there is no permeability given? Who asked that question? I'm going to answer that question. Okay, we get a good match right here with the perm of 0.01 the textbook gives us. Let's say we didn't know the permeability. Okay, fair enough? So let's guess 0.02. You see how it moves the data? Let's guess 0.03. See how it moves the data? Okay, now, one thing I can tell you right now is that the fracture conductivity is 500. It doesn't matter where I move the data, I'm sliding up the frac conductivity of 500. Now let's make the data smaller, 0.005. and now we've slid the other way. Okay? You see how once I pick a perm, I'm locked to my frac half length, and my perm and my frac half length hardwire my T sub D coefficient and my reciprocal Q sub D coefficient. All I can do is slide up and down this 500 slope. So it doesn't matter what I pick for perm, I'm locked into my frac conductivity. Now, who can answer this question? Can the permeability be as low as 0.005?
Is this in the fracture?
This is the formation permeability. Can the in other words, I've got 0.005 plugged in here right now. Is it an acceptable answer?
It's still not in line, I guess.
My data's fallen off the curve. This bottom curve is basically my boundary.
So that's effectively infinite conductivity.
Yes.
So no, it's not a reasonable answer.
There you go. So how about 0.003? Is it a reasonable answer?
No. It crosses contour lines.
It crosses contour lines. It's really the same thing happens to the other end. So the answer is yes and no. I can bracket the reasonableness of my permeability. But we can take this further. On this, let's go back to what the textbook told us what it basically was, 101. Now,
You want to see this?
the one thing we can do, and I'm going to enlarge this graph momentarily, is let's pay attention to the symbols. The square is not going to be very helpful to us because that's the end of bilinear flow. The axis marks the beginning of linear flow. Let me delete this, all my data for just a second. I'll just do an undo when I get done. Let's look at this. So I am in linear flow up to this x. See that x right there? It's going to be hard to see when I put my data back on it. Okay? Now, do you see where that x is? Is about where my deviation from my derivative is showing that I'm moving away from linear flow. This gets better. This story gets better when we move to the constant rate. So, one of the other reasons for not having really low permeability has to do with that x. That x says all my data that if I may, I have to make it a little bit lower to make my point. I'm going to make it a little lower yet. If I would have guessed 0.003, because of where that x is, it says that all my pseudo pressure versus the square root of time should be on one line. Because that x says that I'm still in linear flow. That's the end of linear flow. But my derivative curve is showing that it's not. So do you see what I'm trying to do? If I'm saying that this is the bulk of my linear flow, I want to match where my data falls off a linear flow with that x. And watch what happens when I go to 0.01. Do you see now the x lines up with the point where I'm falling off of my derivative? It's a weak argument. I'm going through the argument right now because it gets better when I use superposition. But you could interpret at this point in time that that's my best match, because that's where, using your technique, let's just look at here and see where my data actually, early time, this is my full scale. Where's my blow up? Here it is. This looks like a pretty good fit right here, and then you can see my data tails off. Okay, so this technique, and matching the X all says that that's a fairly good match. Okay, it's not absolute, but you can see if I adjust it too far to one way or too far to the other way, I can obviously say that it's not that. So A, I bracketed it, and fuzzily I nailed it, but we're going to improve how we nail it. Okay? I'm now going to bring in another type curve. Let's get the Bennett constant rate type curve. All right? This was constant pressure, this is constant rate. I'm going to put this data over here to show that it doesn't match. Then we're going to use superposition, and then we can get it to match. I haven't tried this in a long time, so I'm just going to try to copy and paste, see what happens. It worked pretty good. No, it didn't. Okay, I'm going to have to add the data. Select data. And we're just going to use the data, only data we have. That's T sub B X sub F. I got an equation up here. I got a guess it goes to 4. And oops, I didn't mean to do that. That's the title. My X data and my Y data. I don't know why they always put that thing in there. My Y data is my Q sub E data. Don't ask me why this is doing this. Okay. So this is the same data, so these are obviously different curves. Let's be creative here and give them a different we'll use triangles, I like that, but we'll use red and yellow again. Now let's just change it up. Orange. Okay. So this is a different type curve. This is exactly the same data. Now the very first problem we did in this class is we used a visual basic function called superposition. So if the rate varies in a variable rate drawdown, and although this is a constant pressure drawdown, it is also a variable rate drawdown. Let's apply our superposition function. Let's now, from here on out, look at this as, I'm going to use some color coding here. Everything to the left of this line has been what we've been doing, which is top right, top bottom right, right border. Did I get it? Yeah. This has all been constant pressure. I'm going to give myself a couple of columns, and I'm going to start some constant rate. And we're going to start that with our superposition function, superlinear, or is that what it's called? I think it's called super Q. Give me my time array and my rate array.
Do we have a super cube?
Huh?
I mean, do we have a super cube?
We use this in our very first example problem.
No, we don't have a program.
Yes, you do. We used it in our very first problem.
No, I mean, you call the function, but maybe we don't have a
Yeah.
Does everybody have a function? Super cube? Everybody else will get I don't have it.
What's the first problem we did? Example 6.1, right? These 4 data points right here.
Super radial?
Super
Rate time function. Oh, so that was super radial.
Yeah, we
Yeah,
have a
that's
super
what we
radio.
have.
Yeah, we only have a super radio.
All right. You'll need this. I'll get it to you right now.
Dr. Tyler, before we move on, can I look at 2 of your calculations real quick?
How about I do what I was going to do first so that everybody has access to Super Q and they can be working while I answer your questions.
Of course.
You live with that?
That's what I meant. I meant before we start doing everything else.
Okay, so all I have to do is take the worksheet, create a copy, put it in a new book, okay. Is my VB open? What do we do? Write it in class? How did we get super radial? How did you
Yeah,
guys?
you made us write that one up.
Okay. Okay, super radial should be in here. I have a bunch of other stuff in here that don't really need. This is all you need. Why don't you just guys type this in? Super cute. Add this. This isn't Word. Exporting. That's all there is to it. I'm going to put T and rate in, and it's going to convert it. Is that the one? Wait. No, that's not it, because I need an array. I need a linear. What in the world? No, this is all right. Yeah, this is it. That's all there is to it. No, it's not going to put out an array. I have to use this on every line.
Then how would it be superposition? Wouldn't it need an array?
It's going to for each line. It's going to copy the array to that point. I know how it works now.
Okay.
Let me do it and I'll come back. Where are we? Let me invoke it. This is one of those functions that I like to invoke down here because I'm going to do an absolute value of the first one. Equals super Q. I'm going to grab my time to that point. See, I'm going to start from here and get to that point. And I'm going to grab my rates from there to that point. And then I always want to anchor on the first point and be relative to the current point. And that's really difficult to do if I start in the first cell, so I start here. And this is going to be a different time. That doesn't make sense. I'm sure that's right. Let me make sure I got it right over here. Yeah, that's right. Okay. Now I'll go back to the Visual Basic and you can type that in. Super Q.
Did we not calculate pseudo time on this problem?
The pressure doesn't change.
I already asked that question last week.
Yeah. But I'm glad you're eager to use pseudo pressure or pseudo time whenever you can.
It's just kind of in my head, like automatically calculate pseudo time.
We're actually doing a Chapter 9 problem.
Okay.
Right? It's a decline curve. Oh, and I know why the first row is different. This is actually going to be the square root of time. I'll show you what I mean. This has the same fabric as that superposition function we did do in example 6.1, but instead of the square root of time, this will be the in example 6.1, it would have been the natural log of time.
Square root of time, you said?
This function is utilizing the transformation as square root of time, where the one you use in example 6.1 would have logarithms because it was radial. But yes, the result we get from this is a square root of time. It's hours to the 1/2 rather than hours. We're going to have to square it to get time. Okay, everybody got it?
Yep. Working that. Yeah, mine doesn't work.
It's the shortest for loop I've ever seen.
What does QBLF function do?
Don't we?
Because you're going to tell me.
No. It's nothing you need to concern yourself with.
I'm going to delete it. Just be super.
Believe me, you'll never need to know it. I just test out stuff. Everybody's got to have it by now. I'll come back there. Maybe we'll take a break or something like that if you didn't get it. Okay, so that's going to be hours to the 1/2.
Can you go through how you used it again, please? Now that
Okay. I like to start in the middle,
Okay.
not at the first cell, because if you look at in the equation line, I've anchored the first cell. I'm always looking at the array from the beginning to that point relative, and then I can copy up. Okay, but it's really hard to write a cell that goes from B4 to B4. I can't do it. I have to start a cell that goes from B4 to B7 as I highlight data.
I noticed that you do that often, but when we're doing arrays and stuff, you can't obviously start.
I can't highlight one cell and have it go and have it say B4 B4.
Right. Will it matter? Like you're saying, you're picking B4 to B7. Would it matter if you went to B6?
No, all these other points are independent. They're independent. This is just capturing that array to that point.
Okay.
It doesn't matter. Okay. And what I did say that is matter is that this is T to the 1/2. This has units of hours to the 1/2. So we have, if we're going to use time at some point, we have to square this number. And this first number should match exactly this number because you can't, there's no superposition to one point. Oops. See how this number matches exactly that number. But as I move down, they differ. So here I have hours, and then I have the square root of time. Here I have the square root of time, and here I have time. This puts us back in the constant rate ballpark. We are no longer in the constant pressure ballpark. Now we're going to keep moving. What do we do here? We do T sub dx, and we need a 1 over Q sub d. We got rate and time. Actually, we don't need a new 1 over Q sub d. We need a new T sub dx sub f. Okay? And I'm just going to copy and adjust. That's different than copy and pasting. I'm going to use that same time coefficient, but I'm going to multiply it by a different time. Something happened here. Oh yeah, I'm going to pick the scientific. Okay. So we have T sub d's over here, and now we have T sub d's over here. And the first one's going to be the same. But this is my constant rate. I need a new color.
So you have your E at 0. The one that you used, it looked like.
I don't have anything at 0.
Can you go back to what you just had your,
T sub dx sub f?
yes, isn't that E1?
Oh, that looks like 0. I see your point. Let me,
It should be like 0.00001.
It is.
Right?
Let me make it scientific. 4.5 times 7 minus 6. Okay, for right now, I'm using the same multiplier, just so I get some numbers up here. But these are new times. And I forget if I've done enough or not, but let's now look at, we've converted our data from constant pressure to constant rate. And let's move our data from being plotted versus the constant pressure T sub dx of F to the constant rate T sub dx of F. How come that didn't move? Oh, there's two series. Okay, there we go. Now my data's on versus T sub dx of F. And I think I got a second series on here for my, I have to insert my legend just to see my debut. It was weird. Okay, so now I have two type curves, constant pressure and constant rate. Remember when I put the data as it was on over here, it didn't look as good. That's what we're after. But here in a minute, I'm gonna change that because now, okay, I'm gonna start using a color scheme here. On my new stuff, I'm gonna give it a color. What color do we want to give it? Let's go with green. Okay, I like that. So my constant pressure stuff is green. I'm sorry, my constant rate stuff is green. Okay, now, see, we've got this plot right here. What's our blow? I'm tired of looking at that one. We're going to have too many if I don't start narrowing this down. Here's the one we use to calculate our couple parameters, square root of KXF. I'm going to copy it. I'm going to paste it. I'm going to color it green. I just want the border, okay? But now, instead of the data being reciprocal rate versus the square root of time, I am going to plot it versus my superposition square root of time. Let's get there. It's got the old line, and it's got all the data fall below the old line.
Could we take a break sometime soon?
Yeah. Let's take a break right now.
I'm going to go back and check those calculations first. Check the equation.
Sir, can you show your function?
Gene and I couldn't get it to work.
Which function?
Mine says pound name.
Huh?
Mine says pound value.
Which function?
The superposition.
The super Q.
Oh, you want to look at the function itself.
Yes, sir. Has anybody gotten that to work? You're awesome.
Yeah, mine didn't work.
You need a Mac for it to work? Mac wins.
That's usually the opposite situation.
Yeah, that's what I'm saying. Usually it's always messes up.
We had the same problem when we first put in the super radial, or some people had the same problem. If anybody has any idea what causes that problem, where you can put it in verbatim perfectly and it'll give you an error.
Did you wait for the function to come up and then double click once they came up?
Yeah, never. I know what she's talking about. If you type in here, FUNCTIO and I'll call it something else. T as, don't ever click one of those things.
No, I typed it in letter by letter.
You typed in letter by letter.
Yeah.
I clicked those.
And yours worked.
Like after after, like, once it came up, like, I typed in a big A as, and then once my variant came up, then I double clicked on variant. And I did that for count, variant, all my functions. Like, now variant came up, and double clicked variant.
I guess it doesn't make any difference. I don't usually use that. What are the restroom? I'm gonna turn off mine. Now you gotta remind me to turn it on. It seems obvious to me when it's on or not, but I can't remember.
Did you get yours to work? Yeah, I'm way behind. Hey, did anybody catch when he was calculating the match points? What did he use for Q?
So I should have been renaming it. Is that no problem?
That's when I got left in the dust. This equation. Anybody?
I'll look for you.
Yeah.
Is that the XF screw decay? Okay. I got all this and that excess.
Anybody?
I tried to get him to go back.
Yeah,
I remember when
I
it-
didn't get it.
You didn't get it either? Anybody? When you calculated the 1 over QD for the match points? Everybody's left behind.
I'm so
I'll have
behind,
to
like,
try to say about
tried.
30, 45 minutes into it, I'm like, okay.
We'll come back to that, and then we'll never come back to it.
Whenever you guys like redo or we go to another spreadsheet, is all your stuff always come over?
No, I just lost everything.
But my stuff,
When you do what?
Like in my VBA, like say you open up something new.
I've got to
that
be
he sent us.
careful. I've got to make sure that my module is underneath the correct heading.
I didn't know.
That's what happened.
And I feel like I always have to like copy and paste everything like module by module over to my new one.
Wow.
Did you get the calculation when you did this?
Well, it screwed me up on the test because I couldn't find pseudotime.
I
Wasn't in the work.
did,
But he-
but I didn't understand it.
Did you get the pressure derivatives?
He did a derivative of the rate of the reciprocal rate, but I don't have any clue what equation he used.
And he just used
I don't think
original time.
I don't even think it was
So do
legitimate.
you copy and paste over your macros? You know how to do it?
Hey, Dr. Callard,
I'll upload it.
Yeah, text.
you don't even know what I was going to ask you.
What?
When you calculated the 1 over QD match point,
Yeah.
what did you use for Q in that equation?
Oh. There isn't one.
This equation.
Yeah. I want Q over Q sub D. Then I'm going to divide my Q over that, into that, my actual rate into that, and I'm going to get 1 over Q sub D. I just want to calculate everything off to the right. This number right here, in yellow, is Q over Q sub D.
Okay.
And then I get rid of the Q by dividing by Q, and then I end up with 1 over Q sub D.
While we're at it,
Because I've been doing this for a long time.
can I see your
BGA?
square root of k xf, please?
Square root of KXF.
Oh, okay. I understand.
me move over a little bit more. It's the 64.27 equation.
Yeah. Times temperature divided by.
It's using the slope.
Further, can you go back to the delta divided by Q and derivative? My number is a little bit different from your number.
This one?
H column. H. The delta.
H.
Yeah.
That's my derivative. Okay, who's caught up? Nobody? Who's not caught up? What are you doing?
Who's
Trying to catch up?
No, you're not doing anything. Oh, you are doing something.
Do we just have one that has their function working? Who else has that function?
I can upload the function if you want me to. You want me to upload
Yeah, just
it?
upload the module. That way it doesn't give us
That's
any
what I
problems.
started to do.
Yeah. Huh? Yeah. Oh.
You have that equation?
He literally just calculated his
Yeah, he literally just calculated that equation. So we solve for Q over Q2. And then that is the match point.
Probably just something else off.
Can you go back to your
Right here, you get 56 something. You get 4.
He's calculating Q over Q.
That's how you get 54. This equation right here. But then he kind of plays around with the K gas, with the permeability gas. So you find this.
We use 240 from
There. That calculator, because you have the fracture half fracture. Okay, great.
No, I didn't know that. Well, I didn't know. But, I don't know. I mean, I just figured he probably missed those spots.
So what permeability guess did you end
I
up
think
with?
we're still working with 1. I don't know. 0.01.
0.01. Okay. Gene, did you catch where that Q over QD equation came from? And I'm like, well, what's the source? It's in the book somewhere.
That looks like it's from an SPD paper.
Okay, it's on your news page.
Super cute.
It's just a spreadsheet that's blank, and it's got one VB module called Super, and it's got one function in it called Super Q.
Thank you.
I don't know how.
Oh, crap.
Now what?
Now I'm getting some value. I know it works. I know it just.
It overwrote my old superposition module that had the super radio in it.
I took your sheet and all I did was cut and paste just the raw data.
I expected you to copy paste rather than slide the module over.
I copy paste just the raw data into your just complete blank sheet 3, and did the function on just straight numbers, and it's giving me pound values. I know it's something, but
Are you sure you're in a macro-enabled spreadsheet?
I used your same spreadsheet, just the one that's got no data in it with just that, and then I just added straight columns of value.
And you're getting values.
And I'm getting pound
What?
values.
Maybe you're messing up the pound signs.
So would you mind double clicking in one of your, in the row or in the column that it's in?
I don't know the first one comes in the second. Yeah, no, whole lot myself.
I'll invoke it again. Okay? With Windows 8, I can just hit equals and start spelling it. But if you don't have, if you have Windows XP, then you have to go F of X, user defined. And then you can find all the ones that I've got in my modules. And then you have to scroll down to find an S. And super Q, and then you say OK. So that's the other way to get it. Now it's just looking for two arrays. I'm going to give it the time array up to that point, 4 through 10, and I'm going to give it the rate array, 4 through 10. Then I'm going to come back here and edit, make sure that's always anchored at 4. Oops, function 4 now. And that's my number.
Can I see how you calculate the coefficient for the dimensionless with the, yeah.
It's using the perm, or whatever I guess for perm. Right now I'm at the textbook .01.
Just a quick question. I always
Do you open a new module?
Yeah, I opened up like just the spreadsheet.
Make sure you're using delta pseudo pressure.
Yeah.
Copy paste it. So raw data gets back for a spreadsheet. And I'm getting pound value.
And it's like showing
It's got to be something like the version of Excel.
But it should be.
Only if I do it in the sheet you gave me, it works.
Yeah.
It works in the sheet you gave me?
Yeah, the one
Yeah.
you downloaded, it works in there. Maybe if I export it and then import it into my other one.
Should not be this difficult.
It's just a simple drag. It's not a
Respell it. Try that. Yeah, that helps me sometimes. Just respell it. Just come over here and call it Super QX, and then you got to put Super QX down here to return the result. Try respelling it. I can't tell you how many times that solved the problem. Of course, you have to invoke a different function now. And if it works in the VB spreadsheet that I gave you, then just copy the data over to that. Just do a Control-A, Control-C, Control-V, and put everything into a spreadsheet in that workbook. What did you say?
I got the word.
You have to change the variable name too inside the function to match whatever your new name is.
Yeah, I just said that.
Okay.
I click on it.
Cannot save while debugging. Okay, save it now.
My visual basic super Q function returns the variable time as the square root of time. So in order to get time, I have to square it. It's really the superposition of the square root of time. I'm glad to see you're working again.
It just won't work.
You guys don't have the blank space there?
The what?
You believe that blank? Like it'll give you a hashtag on your.
This one right here?
It's like if there's no space between your text and your.
Where I'm at?
If you were just to delete that row, it would get rid of that other. It wouldn't work.
Oh.
That's funny.
So if you have the extra row there, it works. If you don't have it, it doesn't work.
I don't know why.
That's what it is.
Oh, you know what? I figured that out too when we did the super radial. It drags in values that you didn't send it, and if you have a name in the wrong cell, it'll drag it in.
Okay, that's one to remember.
That's all it is.
Okay, make sure there's a blank row above it. What?
Click on the last one.
Nice.
I'm using the same T sub D X sub F coefficient, but instead of multiplying by this time in hours, I'm multiplying it by this time in hours. The first point is exactly the same, 7.69. With this, 6.8 and 6.8 are the same. After that, they'll differ.
That is infuriating.
That works. That's all it was.
Okay, so we gotta have a blank row above our data. Cool. All right, moving on. I'm going to turn on my sound and take off pause.
Can you? Oh, you have it highlighted. Very good.
Okay, we're recording.
So you might repeat then for that.
Okay, for anybody that wasn't in class today, we found out that you have to have a blank row.
I don't. Y'all hear it come through the speaker just one place last time?
Testing. Yeah, it's okay. I think I turned it on, then turned it back off. Thanks for bringing that up. Okay. You have to have a blank row for some reason, otherwise you get values. If I try to take this up one, I'm not sure how to duplicate that, but that would seem to be the problem. Okay, so now I'm at a point where my green graph, the line no longer fits it. So these are both absolute equations. Let's move them over here. I thought they were both absolute. They're not absolute at all. How did I copy that down? I think my intercept, which I've never used, must have been wrong. Normally I absolute these, copy them down, and then change for this from slope to intercept. There might have been some subtle error in my graph before. Now I am going to copy paste these. I'm just going to copy one of them. I'm going to color in green. And the slope is now going to use, instead of reciprocal rate square root of time, it's going to use reciprocal rate this superposition square root of time. I'm going to get a new slope. I'm going to copy that slope down to this intercept and then respell slope to intercept, so I have a new intercept. And these XY values I'm going to copy over. And make all kinds of adjustments. I want to use my new slope and intercept, but I want to come back all the way to 0 to get my time. And I'm going to color these green. And then lastly, I'm going to change the line of my graph to be the green points. Voila. After all that, my data goes through my data points. So I have two graphs. One's 1 over q versus time, and one's 1 over q versus, 1 over q versus the square root of real time, and one is 1 over q versus superposition time. This is not Bennett figure 11, nor is the other one. That's the trouble I get into when I copy graphs. Okay, so these two slopes are going to be different. And if you look at my PowerPoint here, you can see that for the constant pressure solution, from a dimensionless standpoint, you have 1/2 square root, cube square root, 1/2 times pi to the 3/2, and over here you have the square root of pi. These slopes are going to be different. And we have a different equation for, now we're kind of done with this. These things I didn't have you very convinced of before are going to become more convincing. Okay, so now I want to do most of this same thing again with K and X of S, but I want to do it in green. Okay. Square root of KXF, I have a different equation. Instead of 64.27, we're going to use the 40.93, the one right out of the textbook. Except I've got to remember where to put my delta pseudopressure. I think I know by now. Okay, so now I'm going to use this slope instead of this slope. This square root of KXF is using my reciprocal rate square root of time, and I want to use this one, which is my constant pressure, constant rate. So now I have 40.93 times 460 plus reservoir temperature divided by my new slope times H times, open another paren for my phi mu C sub t, because I had to raise that all to the 0.5. And I close my denominator, and I forgot to divide by delta pseudopressure. Okay, so now instead of 90.1, I have a different number. We'll argue about this later. I have a different number. I am using the same data, okay? I'm using the same data. This slope is 4 through 26, real time versus reciprocal rate. This slope is all the same data points, but now I'm using superposition on the time, and I'm converting the constant pressure data to constant rate. You'd think they would be the same, but they're not. Okay, so now let's proceed with this same theory of guessing a perm and calculating an X of F. And so instead of 901 feet, they're pretty close to being the same. I get 850 feet for my frac length. That means in my equation for my T sub D X sub F multiplier, I'm going to F4 everything here. Copy it. I left something out. I thought I already did this. Oh, yeah, okay, I got the same number, but I can't use that same number because I have a different frac half length. 850 instead of 901. So my T sub dx sub F is now a little bit different. This is green. Now let's look at our type curve. Oops. And then let's play with perm for a second, and then we're going to put a derivative on it. And we'll be done. let's play with that perm on this one. Let's shade it as 0.015. And it should have moved the data, and it didn't. Oh, because I know why. Because I don't have my T sub D X sub F. I was wondering why I didn't do that. I'm using that X sub F. I'm also going to use this perm. Now when I change this perm, I'm still not sliding the data. I have to have my own Q sub D, don't I? Either that or, yeah, I want to have my own Q sub D. This Q sub D column this constant has to recognize the perm for that I want to play with over here. And that's what I want to be plotting. I didn't think I was going to have to do that. Okay, now I should be able to move the data. Ooh. That's right. That's not right. Although I don't see what's wrong with it. I should be able to slide that data like I was before. See, it's only sliding it up. It's not changing the X. I see what's going on. My T sub D X sub F is capturing the wrong term. But it's not. How about this? Here's my problem. I have this new coefficient. I'm not even using it. There we go. Now, when I change the perm, it should slide it. That's what it's doing. It slides it. Okay. So these are mirror images of these equations over here, except for that they're driven by this perm and this fracture half length, and the interrelationship between this couple parameters is different. It's 90.1 instead of, I'm sorry, it's 85 instead of 90.1. So if I have perm of 0.01, I have 850. Okay. This is the moment we've been waiting for. Now we're going to calculate our derivative. the set middle one, yeah. Yeah, everything should work. And I'm going to plot that derivative on my type curve. It doesn't look fantastically better. In my opinion, it does look better. I don't know why I can't. I think the argument is much better now. This is what I've been trying to arrive at all night long. I'm trying to find a linear portion of my derivative. And I can't do that. And I think I can have an argument that trying to get them about the same size. I think I have a better argument that I can find the data that I want to use in my reciprocal rate square root of time, whether it's superposition or at real time. It looks like, you see, from data points 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I'm pretty flat there. In fact, I'm much flatter on my constant rate solution than I am on my constant pressure data. And also, I've really kind of ignored this, but it doesn't really look like my early time data on either one of them is great. So I'm going to drop the I'm just going to read these numbers and decide which ones to use here. I'm going to go from 464 to 973. 464 to 973. You see, this is becoming a little easier for me to pick my data points. Now, for my slope equation, right here, I want to change my array size just to be the points that I'm flat on my derivative. And just to be fair, that doesn't help me. Just to be fair, I should do the same thing for my constant pressure one. I'm going to do that in a second. I want to slide this to the left a little bit, just a look, and and this will way to the right. So I'm trying to answer that question. Can I come up with perm and X of F individually when I truly only know the coupled parameters? And it's a fuzzy yes. I can bracket it into a fairly tight range. And I think my best guess is not the .01 that they gave me, but a point like a .007. That looks pretty good for my fit on my constant rate type curve. Now, I've got a final test here. And at the top of the hour, I told you only in the constant rate solution can I calculate CFD. I can witness it on my type curves. I know that it should be 500 in all the cases we've looked at. We'll make one more calculation, then we can call it quits tonight. But I'm going to use this equation to calculate my frac conductivity How come it didn't take? Nothing's taken. You got the wrong object. Format object. Okay. Let's use this equation. We're working down with these numbers right here. We can't see them all. Let's get up here where we can see everything. I'm going to slide this all the way over here. This is what we're going to calculate it. Okay. Pi over 3, I got that. 1442 T K H Q over delta pseudo pressure intercept. Here is the intercept of my graph, and that's just a 1 over Q. Let's get our term. Let's try to build this term. I think it's going to be equal to 1 over Q intercept I'm trying to combine it with my delta pseudo pressure. I think that if I took, I'm going to do it in 2 steps. Equals 1 over my reciprocal rate intercept is a large number, Q, and then take that number and then divide it by my delta pseudo pressure. There we go. I think that that's my Q over delta pseudo pressure intercept. So now let's calculate CFD. Equals pi divided by 3 times 1422 times 460 plus our temperature divided by KH. K times H. I know I'm not going to get a great match, but ooh, huge. Of course, there's no difference between 500 and that number. Let's just see what we do with the number they gave us. Not positive, but I got everything right here. Pi over 3, 2422 T over KH Oh, I have multiplied by my intercept. Here we go, 345. That's a number close to 500. And if I want a little bit smaller on this number, I'm getting 0.493.
How'd you pick the intercept again?
The intercept is right here. Okay. It is, I'm glad you asked that question because let's emphasize that. I'm going to zoom in some more on this. Okay. Now remember, I actually am not using the first 3 or 4 points. Remember that? Based on my derivative. When I pulled up a shape line and put it through my data, I missed the first 4. So then you can see my data is going perfectly through my next few points. Now you see there's an intercept. This intercept would be 0. It would be the origin if we had an infinite conductivity fracture. Because by my equation up here, if my, where is my equation? If my intercept delta pseudopressure over Q, if it was upside down, was 0, then the reciprocate of that would be infinity. Okay, I would get an infinite conductivity fracture if I went through my origin. But you can see now, I'm trying to boast the attributes of using superposition. Even though we got pretty much the same answer, we had a fracture conductivity of 500, we could bracket them both the same, but when I use superposition, I actually have an equation that allows me to calculate the frac conductivity from the intercept of my graph. And I have an auxiliary way to check all of my data. 493 basically is 500. Can I get the perm without knowing one or the other? I think the answer is yes, because even if I use the textbook perm, watch my data move on my type curve of 0.01. You see, I'm on the line somewhere, but not on the line other places. The textbook that the perm that they gave us of 0.01 really isn't that good of a match. And even though I'd have to say that my frac conductivity is very high and close to 500, see how that lowered? I could actually use gold seed. Where is it? I could set this number to be 500 by changing my perm. I was using 0.077, now it's 0.069. That's what the machine is telling me my best perm is. Okay, so I've gone in a pretty big circular argument. I can actually get gold seed to tell me what my perm is. It's 0.69. I've got a perfect match on my constant rate type curve. Also, I'm showing that the data should be linear between my two x's, and that's the area that I've selected from. I'm not selecting data points outside of that region. It looks to me like I might be able to go a little bit further than I did, but that derivative bothers me a little bit. That's the way I wanted to end this lecture. Pretty much on time. So, we've looked at this every which way we can. We looked at the raw data. It was a constant pressure solution. We had a constant pressure type curve. We do not have that final equation for the constant pressure solution. And I can tell you why we don't have it. basically Q sub D is 1 over P sub D. Oops. But do you see that I want to highlight it.
So that's an equivocation we can make.
We can't reciprocate the right-hand side of this equation. We can reciprocate the infinite conductivity. If I drop that second curve, if conductivity is infinite, there is no second term. See that? But I don't have an equivalent solution in the Q sub D because there'd be a third term. It's like if we, even though the slopes are different, it becomes a snag to try to reciprocate this. Anyway, it's been tried. But only in the constant rate analysis can we get a numerical calculation for fracture conductivity. And this is just an aside, but a lot of people look at bilinear flow. That's quarter root slope data. They'll have it in the textbooks, but it's usually in the field unanalyzable because it's masked by your water production from your cleanup stage of your stimulation treatment. Theoretically, you could get frac conductivity from that bilinear flow period, so there'll be textbook examples of it. But this is a better way to get frac conductivity because when you're in linear flow, you're past multi-phase flow of water and gas. You should be producing just gas and water vapor. So the intercept that you're getting from that line to get frac conductivity, this thing that we just did last, field-wise, is the most reliable technique to get frac conductivity. And we don't have to be constant pressure or constant rate. The superposition function can handle variable rates or variable pressures. The only thing we have to remember to do is, where's my equation? I'm going to delete this one because that's the one for constant pressure. I'm going to have to zoom out to find it. Here it is. So this becomes a powerful equation for analyzing variable rate, variable pressure situations. We plot delta pseudopressure versus Q. We're assuming both PWF can change and Q can change. But we don't plot it versus the square root of time. We plot it versus superposition. So any variable rate, time history can be converted. We can get a time from the variable rate, and then we can normalize each individual rate by plotting delta pseudopressure versus Q.
But that superposition time is still in square root hours.
Yes. Then we square it to get real time. So even though we're looking at our textbook examples, this last thing I've gone through is the best way to analyze field data. It works. You can see we can get our specialized plot, delta pseudopressure over Q, although we were constant pressure, so it was just 1 over Q. And it wasn't versus the square root of time, it was superposition time. We allowed the varying rate to change our time. But you can see, even though the textbook probably, this came from a Bennett paper that came out after the textbook was published. So that shows how we took what the textbook intended us to teach us and actually was able to go a step further in the analysis based on post-published work. And frankly, that's as far as you'll need to go for transient pressure analysis for linear flow.
Got it. The modifier for the TD, can I see that real quick? How are you?
I end up because I was getting confused. I have the TD multiplier and the 1/q sub d multiplier have to be using this perm, and for the T sub d multiplier, this perm and that XF.
Which equation is that? That's familiar.
Basically, the equation for Q over Q sub d is right there.
Yeah, I got that one.
And that one is from the textbook.
Yeah.
Oh no, here it is right here.
Okay.
And it has to be algebraically manipulated to get the match.
Right. We did that before.
Yeah. Alrighty. No questions?
Oh, yeah, we have questions.
Okay. Go ahead, fire.
Did you want to start?
Well, the first one will be easy. We don't have to worry about dual porosity or naturally fractured reservoirs, correct?
Correct. Because you know what? I never see them. I've seen publications. I'm not saying they don't exist. I've had a long history. I've just never had to work them. Okay? And you can make anything look like dual porosity. That's the real problem. It's a non-unique thing. Okay? So I have found that whether it has dual porosity or doesn't have dual porosity, I can make either solution work, and using dual porosity makes it more complicated. So that's more answer than you really want to do. But there's a reason I don't mess with dual porosity, and there's a reason I don't mess with naturally fractured reservoirs. Now, if someone sends you off to Columbia and says, we got this huge gas field, it's natural fractures, you better have your textbook with you, because I didn't cover it.
I think we might have touched on this last week, but I can't remember. If you don't mind addressing it one more time. When we calculate Horner time or MC time, should we base that on pseudo time or Agarwal time?
You go from time to pseudo time.
Mm-hmm.
Once you have pseudo time, this is a buildup.
Yes.
Once you have pseudo time, then Horner time and Agarwal time both use pseudo time. They
Okay.
never use real time.
Okay. But would you use Agarwal time to calculate Horner time?
No.
Okay.
They're both superposition functions, and they have two different applications.
Okay.
Horner time is for the specialized plot.
Okay.
Agarwal time is for the type curve.
Okay. So do not mix those.
Yeah, they're for two different plots. You do not take the Agarwal time and use it in the Horner time. That's a good question.
That clears that up.
The thing that I didn't go over before the last test that I left out is that we use pseudo time for radius of investigation. But I think I cleared that up. In fact, once you've calculated pseudo time, you could copy paste special values and delete the time.
Right. Right. Yeah. You never go back.
You never go back and use real time for anything ever again.
Yeah. Okay.
So if you keep that in your mind, then you'll realize you'll never use time for anything. Because viscosity and compressibility change, and that they're on the x-axis in our type curves, and they're we have to account for their change. We do with pseudo time.
While we're talking, can you highlight that equation for me, please?
Pseudo time?
No, the one I asked you about earlier.
I don't know which one.
The modifier, the above the TDXF.
The match point.
Sorry. Thank you.
In a fractured well, would the skin we calculate in the pseudo-radial regime?
I don't ever want to hear about skin in a fractured well.
Okay.
It means nothing. It's always -6.
Gotcha.
Okay.
In radial flow, it has true meaning. We're looking for positive values of like 3 or 4. That means that we've damaged, we drilled that formation heavily overbalanced. We have a lot of invasion. We need to clean up that invasion, maybe with an acid treatment or flush, or maybe we need a frac just to clean up, to get past the damage. Or if you drill a well and you have a negative skin, maybe you've hit a fractured reservoir. Okay? It has true meaning in vertical wells. Once you frack a well, skin really doesn't have any meaning.
So if we get a problem where we get a hydraulically fractured well, we're not going to be asked to calculate skin because...
That's right.
That's what we really want to know.
I'm going to have you calculate frac length. But you can see how you can weave around. And I'm really glad I got that email about being able to separate these. Now, you may not be able to be on a type curve or find a type curve that fits, but there's still, if you look at everything, you usually, right away you can start in kind of a triangle or a rectangle and hone it in. And although I don't go to it in this class, you can also look at the physicality of how many pounds you put in and assume that its porosity is maybe 36%. And your frac width's 1/10 of an inch to a 20th of an inch. What is my range of X sub F that way? So there's other ways to even bracket it in from different corners. Usually, if you work hard enough, you can figure out the holy grail, perm. Perm is the biggest driver of anything we need to know. We can create this. We can pump harder and pump more. We're stuck with this. And if it's too low to make a commercial well, then we move on.
Did you have another question?
Let's see. When we're looking at drainage area for a hydraulic fractured well, can we just assume that at the end of the frac tips it's all linear flow, or could you ever have kind of like radial flow outside of that?
In reality, we never have. I've never seen pseudo-radial or elliptical flow.
Okay.
I don't think in this chapter, although when we go to we don't have another class, do we? We have a test in here, then we have break, and then we have the final.
We're done?
Yeah. But I fooled you guys, right? This is chapter 9. This is this technique right here that we ended up with is the technique to handle how you analyze wells that are flowing in for linear flow.
Gotcha.
Variable rate or variable pressure.
One thing I don't really have a good grasp on, and this touches on the drainage area thing, is the X effective, the XE.
Yeah, because I didn't really go into it.
Okay. Do you even want to comment on it at all? Because it's on that Green Garden curve.
The data never breaks to the right; it always breaks north.
All right, that's good for me.
So in terms of permeability, Lucian is far better, the constant rate and constant rate.
Constant rate. It gives us one more equation. We do not have any way to calculate fracture conductivity. We can only work with infinite conductivity. We can get the square root of KXF from the slope, but we can get frac conductivity from the intercept. And although our solutions look fairly similar on our type curves for constant pressure, constant rate, anytime we have variable pressure, variable rate, there's only one way to go. Superposition always superimposes the rate time history to a constant rate solution. There's only one way to go. And it's rare that we actually have a true constant bottom hole pressure situation. Even if you have constant pressure at the wellhead, the rates change, so the calculated bottom hole pressure changes. Because there's less friction with time as the rates reduce. So this last technique is really the way to go. Convert all your rate, time, pressure data using superposition to the constant rate solution. So in other words, you can do decline curve analysis using rate transient analysis.
With some of these problems, they give the compressibility of the formation. Do you want us to account for that in CT?
I'll try to make it obvious on compressibility.
And
If I don't give you formation compressibility,
Assuming
but
you're-
I think you'll always find if you add formation compressibility to SGCG,
very small.
it's 6 decimal places removed. I'm exaggerating here,
Yeah.
but it has no effect.
Yeah. I don't know if we addressed this at all, but if you're just given pure data, time, and say pressure, and you don't know whether to expect radial or linear or bilinear
Type curve,
or
type curve
whatever.
derivatives.
Okay.
Just delta P, delta T. Okay? So, your delta P, delta T will look something like the Green Garden, or I mean the Green Garden. Whose type curve is this? How come I can't find one? But something like this, I think this is just a delta P, delta T, and the derivative. And
On the semi-log?
no, this is a log. Well, I don't know what that is. How come I can't find
So put it on a log plot.
log plot?
Delta
Here
P,
we go.
delta T.
Here's a standard radial type curve. And whose is this? We don't call this Green Garden, do we?
Yeah.
Okay, but obviously, if you get, there's diagnostic slopes. Unit slope is wellbore storage. Half slope is linear flow. A flat radial derivative is radial flow. A flat linear derivative is linear flow.
So on the linear, the two curves would be both parallel, half slope, and they'd just be a space separate a gap or some difference that
Yes.
separates it.
Yeah, I could not give you any data and just give you a log plot and ask you what kind of flow it was. You should be able to know the difference between unit slope, half slope, and zero slope, depending upon the derivative.
That brings me to my last question, and this is something that's kind of bugged me from day one, is when we calculate the derivatives.
We have two.
When we calculate the derivatives, what's the time basis for that? Because if you do just like dPdt, or excuse me, double derivative. Anyways, it's going to look very different if you're doing it just based on normal time, or if you do it based on log time, or based on square root of time.
Well, we want to use pseudo time.
Okay.
If we have it. We didn't have it for this last example because it was constant pressure. It's the radial derivative is delta P over the log of T2 over T1. And the linear derivative is delta P over delta T times the square root of time. Now, because this textbook gave us, if you look at it, basically geometric growth in time of all these examples. You know how it breaks the first hour down into sections, and then there's several hours, and then it goes in lumps of 10 hours.
Yeah.
So the textbook and every problem gave us geometric growth, and that's why I always leapfrog my delta P, delta T, and if I needed to multiply by the square root of delta T, I pick one in the middle. Okay? In reality, if you were given constant time steps, that would also work because it would always be in the middle. But there might be situations where that delta T in the middle isn't halfway in between here and here, and you should actually calculate a new column for T average between the 2 points you're taking the derivative. But I never had to really do that.
How soon do you think this lecture could be up on Coursera?
Every single time I come back to work on Monday, I have to. I mean, on Thursday, I have. It's usually not. 80% of the time, it's not there. Then I have to send an email out to the guy that puts it up, and then if he's there that day, then he puts it back up, and then I usually by late afternoon.
Okay.
But if it's up in the morning, everything went smooth. But that only happens about 1 out of 5 times.
If we had a question after this, but wanted to be fair, could we just copy everybody and send it
Just
to you?
email me. If I think it's a good question and it's a valid point, I'll post it on the news. But I won't respond only to you with
no.
juicy secrets.
Not interested in that.
So since you said you already touched chapter 9, what are we expecting in the next, since we have 2 more exams to go,
Yeah.
and you've already covered everything, so how is it going to look like? Are you
We're going to have it. We're going to have it. The next test is over linear flow.
just linear flow? So
Yeah.
we're not going to touch this.
Yeah. And then my comprehensive exam will be over linear flow, radial flow, and chapter 1 topics.
Oh, okay.
I'll give you some weird data, and you'll have to tell me how much H2S is in that sample. You guys forgot all your chapter 1 stuff. Separators. Now, you got to realize when we're in this chapter, we completely forgot about liquids. Right? Yet all gas, or almost all gas, has some liquids. Separator conditions. I know it's been a long time since we covered chapter 1.
Yeah. Okay. So
on the final, it's going to be comprehensive. Some who here missed chapter 1. There you go. I can't leave chapter 1 off because she won't get tested at all on it. So I'll try to have a comprehensive final over everything we've done in the course. So we've had 2 tests, right? And then we'll have a third. And the comprehensive will be a combination of that because some people missed test 1. I think some people missed test 2, and I don't know whether or not someone might miss test 3. I think someone told me they're going to miss test 3.
So when you say next exam, you say we're going to cover this?
We're going to cover linear flow. We're not going to cover that. That's radial flow.
No, sir. I mean what we did today.
Yeah.
Okay. Everything will be covered.
Example 9, one we did today, 6.9. That's what he's asking. Is that what you're asking?
Yeah. So 6.9 is going to be part of it.
6.9, is that what we did today? Yeah. Yeah, there was one, 6.10 I decided was ridiculous. Example 6.
But what we did today,
Today will be on the test. Yes. Linear flow. When I said not this one, I'm pointing to this because I kicked back to find a green gutter type rate. I'm going to push some.
And do you think there's any
I never took it off pause.
you never took it on pause, like at the break.
Yeah.
Do you think there's any
It's a good thing you were here.
do you think there's a need to go over chapter 9?
Hmm? What?
Do you think that any leads to the brush up the night?
Any leads to go brush up the night?
Any need to go over chapter 9?
No. No, I covered it right there. On the handle, variable rate, variable pressure histories. If you rely on Kaltura, just get with some people that stay up in the class.
Can I get you to go back real quick? I think I almost have all this. I just want to make sure everything I did matches up.
What do you want to look at?
I got that. I got. So can you click on your Bennett and show me what you plotted on it? I just want to make sure what I have.
I got 2 Bennett's, of course.
Yeah.
The data is T sub D versus Q sub D, and then I have the derivative data.
And what was the equation for the derivative version? That's what I'm missing.
Delta P delta T times the square root of delta T.
And then on this other one, is that the same thing plotted? You just make 2 of them?
No, this one is the before we hit green. This is this T sub D versus T sub D x sub f, and this is this derivative.
Okay, so you.
But everything is better in this world. My derivative is flatter for longer. See that? That's saying I got more reliable data. I feel like I did a better job of selecting which XY data to use for my slope. Everything got better when I moved to the constant rate solution.
So I'm with you now. Over here, when you did the new 1/QD.
Right here?
I'm sorry, in your columns over there. The one over to the right, the green 1/QD.
Yeah.
Okay, so you're just taking your new modifier and using it.
Yeah, I'm using my new modifier.
Okay, that's where I got lost. Like I had both, and then I started meshing them together. So you made 2 separate ones.
Yeah.
Okay.
That's because I thought I could get away with just one.
Yeah.
I was running behind pretty much the second half of the class. Can you go over just like the main steps that you did at the end there to kind of arrive at your solution?
These steps are exactly the same as these steps.
I got all
that.
that.
The only thing is I'm using a different time.
Okay, I got all that. Then after you've got your match points, what are the 2 values that are below that brick? Say U, scroll down a little bit, column U.
I have all those.
Yeah, that 0.000165556.
Is the intercept?
That's the intercept.
Okay.
Because it was really confusing for me because I don't have Q, I have 1/Q. So the first thing I did is did 1/Q, and then I divided by delta pseudopressure, which is Q5 up here.
Okay, and the significance of the intercept was?
It's proportional to the frac conductivity. I use that intercept to calculate my frac conductivity.
Okay. And then what were the guidelines you used to optimize your permeability?
I goal sought for my permeability to give me exactly 500 because everything this week and last week was telling me my frac conductivity was 500. I could tell that the author used 500 to simulate his data.
Okay, so ultimately you were just looking for the best fit. There wasn't anything.
Yeah, I was looking for I was grasping at everything I could to try to hone in on permeability.
Okay, so there wasn't any interplay between the 2 methods. You were saying, hey, this one's superior.
This is superior.
Yeah.
It's the only one that gives me frac conductivity from the intercept, and my derivative curves look better.
Yeah. Okay.
Well, I don't have them side by side anymore.
And what are these 2 green graphs that you've got below there?
One's a blow off the other.
Oh, okay.
50 and 5.
Okay. Cool.
Dr. Color?
Yes.
Do you mind, if I understand correctly, so you didn't record the last half part of the...
Correct.
Can you, yeah. So, for now, lost...
So that's why you need to make friends with the class, because some people did keep up.
Yeah. Do you mind to now, taking me 1 or 2 minutes to just show, recall now, show what kind of data you select?
You guys don't seem to get it. The Kaltura thing is like an added benefit. We don't rely on it.
Okay. All right.
You don't nod off thinking that you can just watch it on Kaltura later.
I don't know about these guys. I don't nod off. I just
I
can't
know,
keep
but
up.
I know.
So I watch the videos 2 or 3 times to make sure I get all the information.
Yeah.
Yeah.
You say a lot of key things that you can't pick up until you watch it again, and it's like, oh, okay.
I definitely apologize, but there's nothing I can do for it.
I've got the audio. I'll post it as soon as possible.
Okay.
On both the TD modifiers, you use the same equation on both sides.
What do you mean by that question?
You have, that was the first equation I wanted to see, and I got the one on the green side where you use the LF equation.
Yes.
Yeah.
To get your
It's the same equation.
So you used it on both. Is what I'm
Yes.
asking.
But I have different XMX.
Right. I'm with you there.
That's cool.
That one? What's the derivative? Did you calculate the derivative using the first method?
Now, you guys can all huddle until all your spreadsheets are right. You can all huddle. Huddle. Like, in football, you know how they huddle? And then they go out and make their play? If you all just huddle right now,
Which
you're
one?
ready to
This
take
one?
the test.
What's the derivative?
Also different from this.
Is it?
So before the break, there is no video.
After the break.
So it's after the break we have video.
No video after the break.
No video after the break.
Correct.
Actually, stop working after the break.
Do you have his numbers?
Yeah, that's what I'm trying to correct in this class, is do not rely on the
The
video.
only thing I
But just fast
Yeah.
the second one.
Dr. Color, we didn't get a second derivative QD stuff.
Which one's the your calculation?
He lied to me.
Yeah.
He told me he had it.
I thought I did. I guess I couldn't see it very clearly.
Oh, so that was...
Delta reciprocal rate.
Oh, you used the TDXF as the basis.
Yeah, but it's the square. It's the square root of K5.
Hey, did you do that on the first method too? You used TDXF as the basis?
Yeah.
Okay. Interesting. Okay.
Stay there 1 second, please.
So then that's there, and there to the 0.5.
Now you've taken a picture of the one we don't use.
One we don't use.
We use this one. It's the same equation.
I still got different.
Yeah. Take pictures.
Yeah. I'm taking a picture.
Pictures always good. So pick out one and then the others. So.
Oh, and he used the QD mesh, or the QD mesh list also. Okay. So that's
Everybody has somebody else's phone number, right?
got it.
Can't see signature. Oh, this is this one, right? I think to use a 37
Send me an
or still use this use a 37.
I don't have the same numbers he did because I wasn't following tightly along. And it was 0.069.
Frankly, click on the T.
On what?
T, the K column. Yeah.
There you go.
Now, this time right here is just the superposition times squared.
I'll show you.
That time is superposition times squared.
Which time?
This time is the superposition time squared.
I mean, the first column is the K column. The first row. Yeah, now.
This is my T sub D multiplier.
Okay.
Dr. Keller, you know Bruce Heath?
Yeah.
He's one of our consultants, and he just said he's worked with you in the past.
Yeah, we used to work at Woods together.
Oh, really? Yeah, he asked what cleared my present or OU. So he worked with you.
It's mostly commission work these days.
Bruce?
Yeah.
Yeah, that's what we use him for.
I had it and then I jacked it up.
Do you mind I see 1 over QD for the last L column? Oh, divided by D.
I have all of them if you want to go, Dr. Keller.
It's the green columns are exactly the same as the columns from last week, except for they use a different time.
Why do I have 10 times that?
Okay? Listen, drop everything. If I would have taken last week's spreadsheet and added a column, added just one column. See, I made this way too confusing. All I really needed to do is add one column that took the superposition of time. And then from there on out, accessed it. I would have been done. I did it this way to compare and contrast as I went along the difference between the constant pressure and the constant rate solution analysis. But there's nothing new. There's no equations except for the one intercept equation for frac conductivity. All the columns are exactly as we did last week. It's just dimensionless time versus dimensionless reciprocal rate. Exactly like we did last week. No difference. Except now we're using this time instead of this time. Okay? That's the only difference.
I click on the M. One column.
That's the derivative. Yeah, I think I've hovered over every cell twice.
Is there a good pizza place?
New York pizza.
Yeah, it's real close. It's pretty good.
New York pizza. Where's it at Cricket
You
Grove?
can't miss it.
Campus Corner. You've been over to Campus Corner?
Where's Campus Corner?
Oh my gosh. Let's go get some pizza.
I don't know. What's on that?
Like where Louis.
Yeah, okay. I know.
Okay.
With what?
The city.
No.
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 Go down,
No.
and then Crooked Crest.
All right. Try some.
Do you like that?
I like Crooked Crest because you can get like a bunch of different stuff all the time for free. And then they help you share it, so they're pretty good. It's really good. It's different.
I've got 6.9 I got 6.8. I think I do 6.7.
Okay.
I'm maybe one together. Sunday.
Oh, you mean
Probably Friday. If you want to do it Friday.
I'm all over Sunday.
Let's do Sunday, and what I would suggest is we go through the 4 problems.
It's
They're
the
already worked out.
specialized
We just
plot
go through
of
30 minutes, just boom, 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 boom.
Yep.
1 over
That'll
Q
be 2 hours.
versus
And then
the square root of
we
time
do
or the
this,
square root of superposition.
his last thing.
That gives an
Square root
intercept.
K, X, Z,
Yeah.
and better.
Now,
And those two
so
things
this is upside down, so this is Q. So that Q is equal
I
to
give you a graph.
1 over Q. At the intercept.
Okay, so intercept.
Yeah. Yeah, you have an equation of intercept. Exactly right there. Reciprocate.
Okay.
Is that Q? And then it doubles to the pressure, it's just your doubles to the pressure.
Oh, I see. So then it's like
Okay.
this table talk, thinking stuff.
If you were to actually get graphs, it's helpful. But